correlation coefficient is the correlation between two variables, and it measures the strength of a linear relationship. Here's the equation for correlation coefficient.
The 1 over n in the equation tells you the direction of your correlation, whether it's positive or negative. The numerator of your equation gives you the direction of your correlation coefficient. The denominator of the equation is the standard deviation of the two variables. Standard deviation is the measure of how spread out your data is from the average or mean value. The larger the standard deviation is, the weaker your direction will be because your value is closer to zero. The closer your R value is to zero, the less linearity there is within your data. The closer your correlation is to -1 or 1, the more linear your data is. If the standard deviation is a small number, the direction of your correlation will be stronger because your value is bigger. The variable n in your equation stands for the number of data points you have in your study. Here's how to find correlation coefficient.
We'll start off by using the example of finding a correlation between the number of trees and the depth of snow. You first want to start by entering your data into list 1 and list 2 of your calculator. Once you've entered your data, your calculator will give you x bar and y bar values that you will use in the equation. In this case, our x bar is 50 and our y bar is 30.5.
X bar and y bar is the mean of all the x points and all the y points.
Next, you take your value of x bar and subtract that from the values of x from your data. You will also do the same with your value of y bar and subtract that from the values of your data. By doing this, you can see how far your data points are from x bar and y bar. After doing this for each data point, you will multiply the x and y values from the equation above. Multiplying your x subtract x bar and y subtract y bar values will give you one orientation in relation to x bar and y bar. Once you've multiplied each data point, the final step is using the equation to find the correlation coefficient of your data. In this case, there is a strong positive linear correlation between the number of trees and depth of snow.
Chi-squared measures the theoretical probability versus the actual data. The symbol for chi-squared. Same data we used for correlation, we're going to find chi-squared. First, I made an observed data chart with one category as x is less than or equal to 50 and one with x is more than or equal to 50. On the other side, it was y is less than or equal to 30.5 and y is greater than or equal to 30.5. So hold on. We used 50 and 30.5 because that was the x bar and y bar of the data. In an observed data table, you need at least 5 points for chi-squared to work, but for the sake of explanation, we're just going to use the data we found. To find the expected value to compare it to, we have to multiply 6 divided by 6 times 6 divided by 6 times the amount of data points. So that's here. And that equals 10. For the example of this next category, we do 0 divided by 6 times 0 divided by 4 times 10, which equals 0. We did that for every category, and we found this to be our expected data. Then we do the observed data minus the expected data squared so that it becomes positive. So with this example, 6 minus 10 is -4, squared is 16. Then we divide it by the expected value, which is 10, and we do that for all the data points. To find the chi-squared value, I added all these numbers up together, and I got 5.2, which is our chi-squared value. Degrees of freedom is calculated by number of columns minus 1 times number of rows minus 1. So if we just take one out from each and then multiply 1 by 1, we have 1 degree of freedom.
Go.
Because the purpose of calculating chi-squared is to find the level of certainty for which we can be sure that it's independent, we compare it to the critical values of x squared table. So with 1 degree of freedom, we look over at the 1% certainty level. Here, 5.2, our chi-squared value, is less than 6.63, so we can be certain that it's independent on the 1% level. Then we go over to the 5% level. Because 5.2 is more than 3.841, we can't be sure that it's independent at the 5% level or the 10% level, because 10% is more than 5%. So all we can say about this is that at the 1% level, we're sure that it's independent, but at the 5%, it appears to be dependent.
Go.
Because the purpose of calculating chi-squared is to find the level of certainty for which we can be sure that it's independent, we compare it to the critical values of x squared table. So with 1 degree of freedom, we look over at the 1% certainty level. Here, 5.2, our chi-squared value, is less than 6.63, so we can be certain that it's independent on the 1% level. Then we go over to the 5% level. Because 5.2 is more than 3.841, we can't be sure that it's independent at the 5% level or the 10% level, because 10% is more than 5%. So all we can say about this is that at the 1% level, we're sure that it's independent, but at the 5%, it appears to be dependent.